Hi everyone, and thank you for attending this presentation. I am Gianmarco Villani, and I'm going to show you an energetic approach to predict the elliptical crack growth. I would like to start with the aim of the work. We know that for simple geometries and kind of loads, it's easy to simulate the fatigue crack growth considering a stress intensity factor approach. But what happens for complex geometries, complex loads, for example in presence of a bending load or multiple cracks? So, the aim of this work is to develop a method to follow the crack growth based on an energetic approach. Thus, keep going to the hypothesis of the method. The first hypothesis regards the geometry. The initial crack is elliptical and the crack maintains its elliptical shape during the crack growth, even changing aspect ratio. The second hypothesis considers the minimization of the elastic strain energy as driving force for the crack propagation, with the elastic strain energy calculated at equilibrium states. I have said that the crack is initially elliptical and maintains its elliptical shape during the crack propagation. So, imposing an increment of area delta A, it's possible to consider several new crack shapes that are candidate to be the new crack shape for the propagation. The crack shapes are elliptical and with different aspect ratios, but each one has the same area increment and thus the same area. The second hypothesis regards the driving force for the crack growth. At the equilibrium state, the potential energy is equal to zero, so the elastic strain energy is equal to the work done by the external forces. Therefore, it's possible to consider the elastic strain energy as driving force, looking for the minimum value that corresponds to the minimum amount of energy required for the crack propagation, and that corresponds to the new crack configuration. So, starting from an initial elliptical crack and imposing an area increment delta A, several crack shapes can be considered and performing linear elastic finite element simulations for each one, it's possible to calculate the elastic strain energies looking for the minimum value that corresponds to the new crack configuration. The procedure can be automated considering a MATLAB routine and an ANSYS APDL script linked each other to perform the finite element analysis in order to calculate the elastic strain energies and to find the minimum value in order to obtain new crack configurations. The method was applied to 4 different cases. The first is a penny-shaped cracked infinite body, modeled considering the 3 symmetries. The bulk volume was divided in 2 volumes, the cracked volume and the uncracked one. A detail of the cracked volume and the mapped mesh is shown on the right, where the mesh is made with quadratic elements solid 186. The second case is similar to the first, but the geometry is an infinite body with an elliptical crack. Keep going to the results for the infinite body. It can be shown that for the penny shape, an initial circular crack propagates maintaining a circular shape, in accordance with the literature result on the right. This result can be justified giving a look at the stress distribution along the crack front. It can be noticed that the stress states at the elliptical crack semi-axis is the same, so the two semi-axes increase together, maintaining the initial aspect ratio. For the elliptical crack, the crack initially propagates towards the minor semi-axis, and when the minor semi-axis reaches the same length of the major one, so it means that the crack turns into a circular shape, the crack propagates maintaining the circular shape. Even in this case, the result is in agreement with the literature and the stress distribution suggests this behavior. Indeed, initially the crack has the higher stress states on the minor semi-axis, and during the crack propagation, the stress distribution changes up to have the same stress state on the two semi-axes. So, when the two semi-axes have the same stress state, the two semi-axes can increase together, maintaining the circular shape. The third application regards the surface cracked plate subjected to bending load. The bending moment m was simulated as variable pressure applied along the thickness. In this case, the initial stress state is higher on the surface, so the crack starts propagating on the surface, but during the propagation the stress distribution changes, increasing the stress state on the depth semi-axis. So after a while, the crack starts to propagate on the surface and along the thickness as well. The last application regards a cruciform flat plate under biaxial loading. Two different cases were analyzed with different loads, one with the same applied pressure on the two sides and the other one with a pressure that is a half of the other. Only 1/4 of the plate was modeled in this case. Let's analyze the first case with the same applied pressure. The picture shows the beach marks obtained during the crack propagation in the experimental test. It can be noticed that the elliptical crack shapes calculated with the energetic approach are really close to the experimental beach marks. For the second case, with different applied pressures, the same results was obtained. The elliptical crack shapes are really close to the experimental beach marks, even in this case. In conclusion, it was developed a method based on the calculation of the elastic strain energy at equilibrium states in order to find the crack shape that minimizes the energy. The method was applied to uniaxial and biaxial cases, comparing the results to the literature ones, and obtaining a good agreement with the other methodologies and with the experimental results. Moreover, this method allows to avoid calculating the stress intensity factors, thus allows to adopt more rough meshes. So, the shown energetic approach allows to study more complex geometry and non-trivial loads combinations, considering the presence of multiple crack as well. That's all from my side, and if you have any question, please send me an email. Thank you for your kind attention.